Hi, and welcome to 9.3 Conservation of Momentum, Elastic Collisions. In this lesson, students will be able to use the law of conservation of momentum to fully describe the motion of objects undergoing elastic collisions. So, the law of conservation of momentum states that the total momentum of all objects interacting with one another remains constant, regardless of the nature of the forces between the objects. So, even though an object might exert an impulse on an other object and change that individual object's momentum, the total momentum for all the objects in the system, the total, when you add them together, remains the same before and after the collision or when the impulse was exerted. So we have this nice formula, P before equals P after, the total momentum before and after a collision. So where is that law of conservation momentum located on the reference table? Where is it? Where is that conservation of momentum formula? Right here. And guess what, folks? That is the last mechanics equation. We've done all of these equations. We're ready to move on to the next thing. Isn't that beautiful? Wow. Take a moment and start here and look down and see if you recognize all of these formulas. You might say, oh, Mr. Nagel, we never did this. What the heck is that about? Well, that's just if you have a triangle and with a vector A, like this is a vector here, right? And then this is AX, the X component of that vector, and this is the Y component of the vector. And if this is your angle here, then you could use those two formulas as a shortcut to find what the magnitude of AY and AX are. So we've done those before, but I don't really talk about it because what if they give you this angle instead? Then those equations don't really work now, do they? But yeah, last mechanics equation, pretty great. So we need to talk about types of collisions. In this lesson, we're going to talk about elastic collisions. In the next lesson, we're going to talk about inelastic collisions. So for elastic collisions, the objects just bounce off each other in general. So the balls are coming towards each other, there's a collision, they hit each other, and then they bounce off each other. So that's elastic. For inelastic, the objects stick together. So the two objects come together and then they collide and they like lock together and move with the same velocity. They're moving together. So that's an inelastic collision. Elastic bouncing off, inelastic sticking together. That's a way to remember it. Momentum is conserved for both of these. All right. The difference, really, the real difference is that in elastic collisions, I should say for elastic collisions, I always say in elastic collisions, but for elastic collisions, kinetic energy is conserved. All right. The thing that makes it inelastic is that kinetic energy is not conserved. And you might be saying to yourself, wait a second, energy is not conserved. No, this is the total kinetic energy is the same, initial and final here. You have more kinetic energy here and less kinetic energy here, but all that means is that some of the energy is transferred into other types of energy, such as internal energy. Okay, so that's the idea there. Now, the objects actually only stick together if it's considered a perfectly inelastic collision where you get the maximum amount of kinetic energy being lost. It's perfectly inelastic if the maximum kinetic energy is lost, and in those situations they stick together. Technically, you could have a somewhat inelastic collision where they do bounce off each other, but you're still going to lose some kinetic energy to other types of energy. That's the full story. But most of the questions that we do are either perfectly elastic or perfectly inelastic, and you could tell which one is which because for elastic, they bounce off each other, and for inelastic collisions, that's when in the problem they're going to stick together. But I mean, momentum is conserved in both. But for today, we're just going to do elastic collisions. So there are a couple videos in the extension folder, classic Newton's cradle demonstration. Yep, that's fun to do in the classroom. And then you could also have these nice collision carts on this track, and the wheels are near frictionless. So you have these two carts colliding against each other and bouncing off each other with the plunger system there. So again, there's an extension video in the extension folder if you want to check out some classic physics demonstrations with the collision carts. Back to elastic collision. So here's the initial situation. All right, you have momentum for the system. So the momentum of the blue ball plus the momentum of the red ball together is the initial momentum of the system. And then there's a collision, and then they bounce off each other. So it looks like P1 comes to a rest, and all of the momentum is transferred to the red ball in this situation. So the initial momentum is equal to the final momentum. And you want to do this, right? So the initial momentum is the total of this and this together. So we're adding those two together. So a seemingly simple equation expands out to the initial of the two objects together and then the final of the two objects together. But when you add those momentums together, obviously it's the same amount because momentum is conserved. So how can we make it a little bit longer? Let's expand that equation out further. So let's say we know the velocity now and the mass of each object. You could have, the initial momentum is equal to the final, and that's the total of both. But what is P equal to? P is equal to M times V. So for each of these terms, you could have an M times V term. And we have to be very careful with our subscripts so we could keep everything straight. So it gets a little complicated. It's like you have to write all these subscripts out. Check this out. M1 V1I plus M2 V2I is equal to M1 V1F plus M2 V2F. And what if you have three objects colliding? Most of the time it's only two, so we can do it like that. And you see how it's like two separate terms, and then they bounce off of each other. It's elastic. They bounce off each other, and they're still separate from each other. For inelastic, it's going to kind of like combine together because they stick together. So you could write it like this, like we just did. Or sometimes they put this like the prime over here for like instead of I and F, they don't even bother writing the I. So it's more efficient if you use the prime, and that indicates that it's like the final condition. So that's a different way to do it. So yeah, like it's a little bit cleaner for these subscripts near the velocity because you have the initial velocity and the final velocity still. So if you're more comfortable doing that, that's totally fine. I'm going to stick with the initial and the final because that's what we've been doing all year. So here we go. An example. Ball 1, which is 3 kilograms, hits stationary ball 2, which is 6 kilograms, with a speed of 4 meters per second, then becomes stationary. What is ball 2's velocity after the collision? We want to be very careful when we're writing down our given information. So just take it step by step. The ball 1, and they're telling you the mass. So I'm going to, using the subscripts is super important. It's 3 kilograms, and it hits stationary ball 2. Okay, M2, 6 kilograms. All right. Oh, and ball 2 is stationary. Look at that wording. What does that mean? That means what is the initial velocity of ball 2? Really? So we should write 2I. V2I is equal to 0 meters per second. And it says with a speed of 4 meters per second. So ball 1 hits it with a speed of 4 meters per second. That means that's the velocity of ball 1 initially is 4 meters per second. Okay. Typically, I'll write it like this because I try to go in the order of like 1, 2, 1, 2, and then initial, final. Doesn't really matter, but if you're consistent, it kind of makes it easier as you're pulling the information for the equations later on. It's one less thing to worry about because you kind of know where everything is located if you get into a good habit of putting things in the same spot. So it says Oh, then it becomes stationary. So ball 1 hits it with 4 meters per second. That's 4. And then it becomes stationary here. So that means the final velocity of ball 1 is 0 meters per second. And they say, what is ball 2's velocity after the collision? That is the piece of unknown. So you want like two masses, 2 initial velocities, and 2 final velocities. That's what you should get for these elastic collision problems. Not every problem's the same, but like it's in general. So we could, write out, okay, the initial momentum for the whole system is equal to the final momentum. That is the law of conservation momentum. It stays the same. It could transfer from one object to another, as it happens here. Right? The momentum is transferred to object 2, but the total is the same. Okay, so I'm going to skip doing the next line. But here's how I do it. You could do it like this: m1v1i plus m2v2i is equal to m1v1f plus m2v2f. But it gets like really confusing, and you could put an I where you put an F, or a 1 where you think you should put a 2 very easily and not even notice it. So you could try that out a few times. It's good to like practice it and just do it slower than what I just did. Like really think about, okay, it's the mass of the first object times the velocity of the first object initially. But really it boils down to like mass times velocity plus mass times velocity, because there's two separate objects. This is like a really cheat code. Like you're, hopefully you understand what's really going on, and then you carefully do like 1 1, 2 2, 1 1, 2 2, and then remember that, oh, this is the initial and this is the final. So if you want to like build your equation like that too, that's fine. Whatever way you can write these subscripts, that's probably the trickiest part for some people, is making sure the subscripts are all in line. And then once you have your givens here and your equation nicely written, all you have to do is plug in the numbers. So M1 is 3, V1I is 4, M2 is 6, V2I is 0. So sometimes I might even just go like this and not even bother writing this part over here, but just to be quicker. So once you get used to doing that, that's totally fine if the velocity is 0. This is 3, V1F is 0, 6, and then we're looking for, okay, so we're looking for V2F. V2F. Nice. So we have 12 plus 0. See how quickly it goes? That's that whole left side of the equation is 12. 12 kilogram meters per second. That's how much momentum we have to play with for the system. Then this goes to 0, 3 times 0, and you're left with 6 V2F. Wow, how simple is that? So it goes from crazy complicated looking to 2 meters per second because you do the division, right? All right, so there is, if you get comfortable with the idea of, okay, this one has 3 times 4 meter, okay, this has 12 kilogram meters per second, and this one doesn't have any momentum, so I know that there's 12 kilogram meters per second for the whole system. And, oh, that one comes to a stop, so that means all of that 12 kilogram meters per second is in the red ball. And if it's 12 kilogram meters per second, you divide it by 6, and that gives you 2 meters per second. If you could like see the concept there, that's great. But I like to teach it this way because it's a process that you can apply to like pretty much all different situations. But if you can like see the concept, that's a powerful thing too, and you could check your work by doing that. Cool. All right, so a little bit more complicated because now there's 2 velocities. If you want, you could pause the video and check it out. I'll do this one a little bit quicker, I believe. So you write the given information and the unknown, and if you want, you could pause the video and see if this matches up with what you wrote down, because you tried it, right? You tried it on your own first, maybe? I don't know. So I was careful with my subscripts, as you can see, with the initial and the final. And then you're going to write down the equation. Hopefully you have something that looks like that. Sure, you could start out by stating the conservation of momentum. That's totally fine, but not required. I won't make you do that every single time. But it is good to know that is the concept that's going on. The total momentum of the system of these two objects, the total of those is equal to the total momentum of the system after the collision. That's the whole idea there. So then you just plug in your numbers carefully. So just take your time with that step and make sure you're looking at your given information. Take your time doing it. I didn't want to bore you by walking through it the whole time, but it is a process. You have to just take it slow and make sure you're plugging in things where they should be plugged in and all that stuff. And hopefully I didn't make a mistake. If I made a mistake, make a comment below. So as you solve this, really keep in mind, so this is the initial momentum of ball A. Right? It's 15 times 7. So you get 105. Oh, my pen's crapping out on me. You get 105 kilogram meters per second. That's the initial momentum of ball A, plus 5 times 2, 10 kilogram meters per second. That's the initial momentum of ball B. So the initial momentum of the whole system is 115 kilograms. And then you get the final momentum of ball A, which is 15 times 7. Oh man, I didn't even do that on purpose. It can't be 15 times 7, right? I did make a mistake. I called out my own mistake. I didn't even do that on purpose. Man, VAF just shows you how it's easy to like make a simple mistake there. I was like, how could that ball have the same momentum as it did before? It can't be 105 again. No, it's got to be 15 times 4. That's the final. Sorry if that was confusing to you, but I'll leave it in the video again just to show you that it's easy to make a mistake. Hopefully I didn't trip you up too much. You're like, why the heck is it a 7 over there? It's a good learning experience, I think. Or I just don't feel like re-recording it, to be honest. But we'll roll with it. It's okay to make mistakes, everybody. All right. So, and then if I was going to continue this line of thought, so this was 60 kilogram meters per second. That's the final momentum of ball A, and this is 5 times VBF. We're doing like our own momentum equation, P equals mv for this red ball. What is the V, right? So we have to find how much momentum it is first. Of that 115 kilogram meters per second, ball A is using 60 of it. So ball B is using 55 kilogram meters per second. So that's your P. P is equal to mv. See how this, like, it's just really, you don't have to think about this every time. You're just solving, but I'm kind of explaining the reasoning behind this. Like, it kind of makes sense. Oh, wow, look at that. So VBF is going to be equal to 11 meters per second. All right. That's how it works, people. Let's see. What do we got? All right, so this one's a tricky one because it's a student practice one. I won't give away why it's tricky, but I do want you to pause it and give it a shot, and then I'll go over it. I promise this one will be quicker. So you're going to write down your given information, and I can tell you right away, the trick to this one is that ball 2 is moving to the left, and we're talking about velocity. And velocity is a vector where the direction matters. And how do we mathematically represent the direction left? We have to make this negative. Okay, so that's the key for this one. You're going to get the question wrong if you just leave it as positive. So, yeah, make sure if it's moving to the left that you make it negative. All right, here's the rest of the problem. So you could see the momentum of ball 1 is 15 kilogram meters per second to the right. The momentum of ball 2 initially is 30 kilogram meters per second to the left because it's negative. We made sure it was negative. And that means the total momentum of the system is negative 15 kilogram meters per second. That's the whole momentum of the system initially, PI. And then since the ball 2 comes to a rest, all of that momentum is transferred into the first ball. So that's the first ball we know has a momentum of negative 15 kilogram meters per second due to the law of conservation of momentum. But what is the velocity? If it's 3 kilograms, the final velocity, you get a negative number, which is what we'd expect because you should be moving to the left if your momentum is to the left, and you get negative 5 meters per second. So yeah, that's how that works with the vectors. Here's one more. I know we're at the 20-minute mark, but I wanted to show you one where you're solving for the mass. So try this one out. And then here are the givens. And as you can see from the diagram, initially ball B is moving to the left, so you make that negative. And then after the collision, ball A is moving to the left, so you make that negative. So double trick with the negative signs there, but then you're also solving for MB. So here's what that looks like. So after you plug in your numbers, you're just solving. So the momentum of A initially is 40 kilogram meters per second. Then it goes minus, like to rewrite it like this, because you're going to end up solving for this variable, just like you would in any other class, any other math class. I don't know if you solve for variables in your English class or anything like that. You should, though. I don't know if you should or not. So we're going to solve for MB. So how would you do that? You want to combine like terms, okay? So I don't see an MB with this one. I don't see an MB with that one. So I'm going to combine those two. And then this one's being multiplied by MB, and so is that. So we got to combine those two. Isn't that nostalgic? Like you should have learned that a couple of years ago, I think, right? So let's add 20 to both sides. So you get 60. And then let's add 2 MB to both sides. So you get 10. Should I show that? I guess I should show that. Should I? No. Should I? I guess. Yeah, so you get 40 plus 20 is 60. And then you get 8 plus 2 is 10. Look at that, how nice that works out. So 60 divided by 10 is going to be 6 kilograms. It's not going to always work out nice like that, okay? Sometimes you'll get decimals. So that doesn't mean you did something wrong. Just always double check your subscripts over here. To be honest, I messed up a couple times. I could think back to 2 times besides the one that was actually in the video where I did like, I think I put an I instead of an F over here, and I think I put a 1 instead of a 2 over here on the previous step. It happens, so just keep checking your work, especially in the beginning, and go slow. Go slower than what I just did. Just take your time. You could do it. Anyway, that's about it. Thanks for watching, and have a great day.